Okay, hello everyone. It's Monday, February 22nd, and day 14 in terms of our lectures. So let us start eventually. So I recall we have 33 people here. I hope others will come soon. But I recall that we have TA help sessions today and tomorrow at 5 p.m. for homework number 3. And then on Wednesday also, I will have my help session at 5 for your exam. After homework 3, deadline for homework 3 is rigorous because we want to post the solution as soon as possible after this, such that you will have it for your preparation for the exam. Your exam is on Friday, and you know it will be on eCampus, so you will do it by Zoom like we did for the quiz. But now it's mandatory and it's important to take it. And please be serious about it. Please get prepared as much as you can. And the best hint for you how to prepare, do your homeworks and do your homeworks yourself. And when you make sure that you know how to solve each problem in the solution. Again, when I solve some examples and you understand what I'm doing, I appreciate it, but it does not necessarily mean that you will manage it on your exam. Key point, key point that you solve it yourself. So I will still give you some introduction hints in like help session on lecture on Wednesday. So presumably there will be no synchronized lecture on Wednesday because I have another meeting this time, but I'm going to record the lecture then if it's the case, and then I will post it and it will be summary for your exam plus the beginning of chapter 4. But now let's proceed with ideal gas and let's finish the topic because today it's important lecture. I want to show you something. So let me share eventually my screen and let me recall what we are doing. You see my screen now, right? So basically what we are doing. So we talk about ideal gases, right? And key points that you remember about ideal gas, two things. What is physically ideal gas assumption? It means that particles don't interact and particles don't have size, right? From which it will mean that, yes, definitely I will tell you on Wednesday if there is lecture or not. Yes, I will definitely. Definitely, you're right. Yeah, definitely. I respect your time, so you should not wait for it. But again, why don't you listen? If lecture is recorded, why don't you listen to it in regular time rather than later? Because if later there is a chance that you don't listen it. Anyway, ideal gas. So basically, from these two assumptions, it follows that latent energy is much less insensible, which actually means what? It means that your particles are free. It means that its temperature is the only measure of ideal gas. It will actually mean that what? That your internal energy and your enthalpy are functions of temperature only. That's what we have, right? And basically, what about that is physics. Mathematics, what we discussed. That ideal gas, you know, it's ideal gas law. Sometimes we call it Mendeleev-Clapeyron equation. There are many ways how it may look like. So it is that PV is equal to, it can be written like NK Boltzmann temperature. It can be written like this through universal gas constant, like this, like this, like this. We all discuss it, right? We all discuss all the parameters. I don't want to waste more time on it. But if you divide both sides on mass, or so basically you come to equation like this: PV is equal to mRT. When I is specific gas constant, don't confuse it with universal. It's from your table. And if you divide both sides by mass or volume, you come to that equation that we have. So this is our equation, right? And that's what we know, that's what we discussed. And we say that, you know, all happy families are happy in the same manner. So all ideal gases obey this equation that we have. But key points that we discussed last time, you know, we are engineers rather than mathematicians, right? That in reality, of course, there is no ideal gas. So we introduce a way how we can count it. So basically what we have, that equations like PV is equal to like is still ideal gas, right? It's still ideal gas equation. But equation like let's say it's not ideal gas equation. Why? Because of this factor. This factor is what? This factor is Z. It's compressibility factor how we introduce. So in fact, we can see the equations like this. Correct? When Z is a compressibility factor. And what we say? That Z value is from 95% to 100, it's ideal gas. Otherwise, we say it's not ideal gas. Remember, we discussed it. Right? So what is Z? It's actually our actual volume divided by ideal volume. That's what we discussed. And then we realized that, okay, that if pressure tends to zero, then of course you approach ideal gas, right? Because if you're one person in a vacuum, you're definitely ideal. There was nobody worse than you. You are brilliant then. So pressure tends to zero, you approach vacuum. But at high pressure, it's not ideal gas. So its factor Z shows deviation from ideal gas. And we realize, remember, that what happens? That far away from at rarefied flow, you have ideal gas. Far away from this compressibility bell, you have ideal gas. But you definitely don't have ideal gas here, don't have ideal gas here, don't have ideal gas here and here and here. So please, and that's, again, I tell you one more mistake the students do. Okay? We deal with ideal gas before your exam. For some of you, or those who don't attend my lectures, you think you remember ideal gas law, so whatever you come to the exam, you employ ideal gas law for anything. That's wrong. So most substances you deal with, it's not ideal gas. Water vapor is most likely not ideal gas. Freon is most likely not ideal gas. And even superheated vapor that you deal with, most likely it's not ideal gas. And for sure, solid, saturated mixture, saturated liquid, compressed liquid, definitely it's not ideal gas for sure. Even superheated vapor most likely is not ideal gas. And to use ideal gas equation, well, air is typically ideal gas, but to use ideal gas equation, you should have some hints. And finding factor Z give you this hint. So what we know about factor Z? We know about factor Z that it should be far, that to have ideal gas, you should be far away from critical point. So it will happen that your factor Z depends on how far away you are from critical point, correct? So your factor Z appears what? Your factor Z appears a function of reduced pressure and reduced temperature. Okay? I recall what it is. So here is critical point. So it contains critical pressure and critical temperature, right? So you introduce scaled properties. Reduced pressure is nothing but your real pressure divided by critical. Your reduced temperature is nothing but your real temperature divided by critical temperature. Here is the value. True? So the ratio gives you reduced pressure, reduced temperature. Here it is. You put it here. You put it here. So then you calculate Z and see if it's far away from unity or not. And based on this, you make your conclusion. So why it's like this? Why it's like this? I told you, because when you do this appropriate scaling, then all different gases come into one curve, right? They resemble. All other gases are not the case. So definitely that it is. And that you see why they collapse into one curve. Because remember I told you last time example that mice on my table behaves like rabbits in a basement, like deer in a backyard, and like elephants on a stadium. They all look, if you zoom them, they all look like gray points, right? But definitely, if you put the elephant on my table, it will not be mice. And if you put mice on a stadium, you will not see them from airplane. So that scaling, we can see that. And basically, I solved this example last time. Remember that how, for instance, the question is how to check if you have 200 Kelvin and 132 bar. So is it ideal gas or not? What we do? This is the example. Well, this is the example. So you go to your property tables, you find what is your pressure, what is your temperature. You have it here. Then you find what is your critical pressure and critical temperature. You arrive that your critical temperature will be 133 Kelvin and your critical pressure will be 37.7 bar. So when you scale them, you arrive to reduced pressure 1.5 and your reduced temperature, reduced temperature 1.5 and your reduced pressure of 3.5. And when you have them, what you do? Then you find Z Where is my reduced pressure? It's this line. Where am I reduced pressure? Here. So that's what you get. You get that UZ is 0.8, which gives you what? Which gives you that this is not ideal gas, right? Because 0.8 it's not 0.95. It's not unity. Does it make sense? Well, in your homework, you have problem number 6, which about to be the same, so you should solve it. And that's something I can give you at your exam. Well, of course, it may be different problem. For instance, I can give you reduced pressure and Z factor and ask you to find T. Or I can give you T and Z and ask you to find reduced pressure. Or to more complex, I can give you temperature and Z and ask you to find pressure. So it's not like critical value. You should be able to scale it and then reproduce. That's something important. Okay, does it make sense? So basically here it is. And also we recall last time that of course when reduced pressure tends to 0, then you tend to ideal gas. But otherwise it's not the case. And you may see that in fact what this diagram shows, it's competition between sensible and latent energy. You understand somehow pressure is latent energy. It's interaction, right? One particle doesn't have pressure. Temperature is sensible energy. So what I see at first plot here, I see that my reduced temperature is 2.0. What does it mean? It means that sensible energy here dominates over pressure. It's high temperature. So I have ideal gas all the cases. But if you took reduced temperature like this, 1 or 1.1, what does it mean? It means that definitely here it's ideal gas and here it will be ideal gas. But here the pressure is high and the temperature is not high enough. So latent energy dominates over sensible, and this is not ideal gas, and the factor is small. And I recall you last time we discussed, and that's very illustrative example, that remember that water vapor at 11 bar behaves like ammonia at 5.6 bar, behaves like carbon dioxide that we breathe out at 3.7 bar, and behaves like air at 1.9 bar. For all these cases, we have what? For all these cases, we have reduced pressure to be the same, to be 5%. That's really illustrative example. That elephants on a stadium behave like deers on a backyard, like rabbits in basement, and like mice on a table. So temperatures are different. And that also shows you why water vapor is most likely not ideal gas, right? Because 11 bar is 11 atmospheres, it's far away from what we have. But air is most likely ideal gas that we have here. And you may also realize from here that if I look at this diagram, of course, all these points collapse into one curve because it's reduced pressure and reduced temperature. But otherwise, this is not the case. If I plot real pressure and real temperature now, all methane, ethylene, ethane will differentiate, right? Elephants will require the stadium and mice will require a table, if it's good illustration for you. Okay, any question at this point? Okay, then let's do a couple of examples. And in fact, there is very good illustrative in your textbook. I will not actually solve it, I just show it. One good illustrative example from your textbook is example point 311. You will see it now on my screen. So basically, and what happens here, it's very, very illustrative too. That's why I want to show it. Okay, there are several methods how you can calculate something. Please look at it. And basically, what do we talk about here? We talk about the following. That you have freon. Okay, you have freon at 1 megapascal and 50 degrees Celsius. Okay, and the question, and you are requested to find specific volume at this point. And there are various ways how to do it. So how shall we proceed? So what should you do? And I tell you what you do typically first in that case. First, what you do, well, and now you should realize, we talk about freon, which is not mostly ideal gas. So don't use ideal gas unless it's not justified. So what you should do, you should go to tables. So method 1, you should go to tables, okay? So which table we should go to? What table? So at this point, actually, you don't know what table, right? You don't know what table to use yet. So basically, I recall what we do. You assume, well, maybe last time, you assume it's saturated mixture and check. So what you will do? You will plot your classical, what? You will plot your classical diagram. So you PT diagram, right? So this is your PT diagram, it's like this. So I will take my pressure, which is 1 megapascal, right? This is my pressure. And I will say, assume this is saturated mixture and check. So what I will do? I go like this and see what will be my saturated temperature at this given pressure. So what is it? Which table should I use? Please help me. So what will be saturated temperature at 1 megapascal? What table am I going to use, by the way? What table? No, not table A5 and white, not table A5. Explain why not. It's okay. It would be table A5 if it was water. But here you talk about free one. For free one, it's another table. But I appreciate your mistake today, not on Friday, because that's classical mistake that you do. You'd go to pressure table, but it will be table A12. Table A12, because it's free one. Well, A11, it's also okay. It's a temperature table. It can be. But let's talk about pressure. You know, if you use table A11, there will be some small problem, because in table A11, there is no value for 50 degrees Celsius. There is value for 48 and 52. You can interpolate, of course, but that we better use pressure. So you go to table A12, and let's find saturated temperature at this given pressure. What is it? Yeah, please. Yes, it's something like 39 points, something like this, 39 point, yeah, 39.4, something like this, 37 Celsius. What does it mean? But our temperature is 50 degrees, right? So what does it mean? What does it mean? It means that we are where? It means that we are here. It means that we are ahead of, so this is your, like say 39, but I'm here, right? So this is superheated because this is 50. So what does it mean? It means that's why it's superheated. It's superheated because it's hotter than it should be to be saturated at this given pressure. So, and then I'm at superheated vapor. Yeah, you're right. You can do it potentially. You can do the same with table A11 and find the pressure, and you'll have rarefied. So it's superheated vapor. What should I do next? I go to which table? I go to table A13. And in this table A13, I will find what? I will find specific volume at 1 megapascal and 50 degrees Celsius. And what the value will be? Could you help me? For bonus or for your own sake? Okay, great. Yes, 0.21746. Yes, so basically what you do, let me see. So you go to your tables, right? And let me actually clean it. And let me go with you for your tables. Here is a table. I go to table, which table? I go to table A13. Let me actually even increase the size of these tables. Let me go to table A13. Table 13. And so my pressure is 1 megapascal. My temperature is 50 degrees Celsius. Here am I. So here are the values that I talk about. And first column corresponds to specific volume. So here is my specific volume, 0021796. Everybody knows how to get it now? Great. And true, that is true. Excellent. So what I do next? Sorry, guys. And that's true. In fact, in your example here, it's shown, this answer is shown from table. Here it is. You see it on the screen? But I decided to solve it because that's what you should do. So what we did now, that's how you should behave, how you should proceed on exam. Okay? Okay. Now, but assume you don't have table. And now I will behave like not very accurate person. So I'm thinking, may I employ ideal gas or not? So what should I check if I can employ ideal gas or not? What should I do? So I should check if it's a yes, exactly. I should find z. So how to find z? Well, there are actually two examples how to find z. One way is the following. You already, so if you have this value, you can simply write that z is what? By default, it will be what? It will be PV over RT. And here you substitute this V value and calculate and get it. You can do it. But in fact, what happens if you don't have this V? Then you should behave, and that you should calculate based on compressibility chart. That's how you do in your home. In your homework, you do both of this example. So what shall we do? So that's the example. So you talk about how to find Z. You should find the critical value, and you should find the real value. So what do you have? So how to get critical value? Again, you have it go to your tables. What do we have? We have free one. And table for critical points is here. So free one, by the way, the correct scientific value for free one is, title for free one, it's tetrafluorethane. You see here it is. I never remember this, and you may not remember here, but here it is. And here is a formula for it, by the way. So it's consists of carbon, fluorine, and CH2. Okay, anyway. So what you see here are the values. Here is critical temperature and critical pressure for it. 0.59 megapascals and 374 degrees Kelvin in Kelvin scale here, right? That's what you have. Okay, great. This is temperature. Well, also in this value, you can calculate this tabulate volume in meter cube per kilomole is specific value, but I would not request you to calculate it because it's different value. So now, what you do next? You know this value, and you know your value. So now, what you can do? Now you can calculate your reduced pressure and temperature, right? Here we are. Remember what we are doing. So this is Z factors. This is your reduced pressure, and this is temperature. So what is your pressure? 1 megapascal. What is your critical pressure? You know it now. What is your temperature? It's 50 degrees Celsius. And now you should convert it into Kelvin. Don't forget, classical mistakes that many students do. You confuse Kelvin and Celsius. And this is critical temperature. So what you will be doing? Here it is. So basically you go back here and you calculate. So again, when you use compressibility chart, you don't need to be very accurate. It's okay to do approximation. So here you calculate reduced pressure, and you will write it's like 0.25, and reduced temperature will be, again, here use temperature in Kelvin, so you calculate about 0.63. Then what you will do? When you go to your charts, to table C, it's table 15. When you have these values, here it is. Basically, since you talk about reduced pressure to be small, you should use this table. When you have small reduced pressure, small reduced temperatures. Well, here it's not very well seen for different temperatures, but you may believe me that in this book you get it. So you will get that your Z is equal to 0.88. So what will be your conclusion from here? Z is equal to 0.84. So what is it? Is it ideal gas or not? No? Yes, it's not, of course not, because it's what? Because it's far away from 95%, correct? It's less than 95%. Correct? It's less than 195. So generally speaking, you cannot use ideal gas. But I will show you something very interesting. So first of all, let's say I'm a bad student and or bad instructor, and I don't care about this. So I didn't make this analysis. So let's say I decided to employ ideal gas law like it is. So let's say I decided to do it. So I used to write and from here I will calculate that V is equal to what I will get. Here you see what I will get. Do you see my screen? Yes. So basically from here you will see RT over P. Here is your pressure from the table, temperature, make sure temperature is in Kelvin. And if you calculate, you will get this quantity. What do you think about this quantity? Is it good? It's small. So that's what ideal gas equation give you. It's ideal, like say ideal, right? So that is your tabulated value, and that is your ideal gas value. So is it good? No. Well, no, it's not good if you may calculate. So if you calculate the error between ideal gas and real value, you will see that your error is like 21%, 20.8%. It's bad. So that it's big error. And it should be why it's like this, because your compressibility factor Z is small. It's not 1. It deviates from 1. So if I am a stupid instructor who just use ideal gas law, definitely I will get very wrong answer. Correct? But there is one way what you can do. So you know what? What I can do instead? That instead of using, instead of using equation like it is, I can use this equation. Potentially, here is my equation. Do you agree? So from here, I can write the following. From here, I can write that my V is what? ZRT over P, right? Otherwise, because what is RT over P? If I calculate this value Z over T, I can write like this. I can write that Z will be actually what? So I can write that V will be actually Z multiplied by V ideal, correct? That's what we have. Remember here, remember that what we have here. Remember, if you have Z is this value, so you have Z is V actual over V ideal. So I can actually write that my actual volume, it will be what? It will be Z by ideal volume. So what I do here, please understand, I am making correction to ideal gas law. So it's not ideal gas, but instead of you, and you know that V ideal, what we have here, it's bad value, it's wrong value, here it is. But what I will do here, I will multiply it by Z, okay? I will multiply it by Z and make a correction. And then if I do this correction, I arrive to this value. And this value is like beta comparison with my table, correct? What is my table? My table give me this value, like 21.7, and here I have 22.1. Is it close? So now the error is only 2%. So that is what we can do. Do you understand? I introduce correction, and this correction helped me to get appropriate answer. Please ask me something. So again, it's your example from your textbook. You can go through it yourself at home, but please understand what we have. So you should use tables. If you have tables, use tables. Don't use any equation because somebody prepared this table for you. And that's correct way. Tabulated value is the best you may have. Now, that was method 1. What was method 2? Method 2 was to use ideal gas law. And you know that this is a bad method. That method gives you really big deviation from correct answer, 21%. So you should not use ideal gas law as it is at least. Why you should not use ideal gas law? Because stated here that Z is 0.84. Because compressibility factor is far away from 95%. So it's not ideal gas. But what you might do, if you assume that equation, like this, is okay, ZRT is okay, then this equation give you more or less suitable result. Does it make sense? Does it make sense for you? I hope so. Now, but of course you may see it's not all, well, even this correction does not tell you all the time, because even equation P, like our equations that we wrote here, PV is equal to ZRT, it's still linear equations that may or may not happen in reality. In reality, we should talk about more sophisticated equation of state. And that's what I'm going to do now. So what equation of state actually might happen? There are other equations of state. And so we will start with simplest what we call van der Waals, but others also will be considered. So basically, what is it and how we arrive to this equation? Okay, let me tell you like this. So, you know, how we approach the ideal gas law. Remember how we derive ideal gas law. We say that there are two physical approaches. Particles don't have size and particles don't interact, correct? Now, in reality, you know that particles do have size and do interact. So do you agree with me that if I want to incorporate more sophisticated equation, I should account for particle size and I should account for the interaction, right? And that's what van der Waals equation gives you. Here it is. So look at this equation. What does it mean here? This term A over V squared that you see, it shows interaction between the particles. If particles interact, it provides you extra pressure. Do you agree? And factor B shows the volume of particles. And by the way, why it's so important? Because remember, we just considered previous examples from the textbook. And you remember that your actual volume was much less than ideal volume. Why? Because for ideal gas, you assume that there is no size particles. In reality, is there. Like imagine you sit in the class. When I have in-person class, I would really show it. And now I will ask you, how much air, what is the volume of air in the class? And definitely how you can calculate. If you neglect your size, you will say, okay, it's like length by the width by height, right? It's a cube. But if you account for your size, it will be that, what I mentioned, minus your volume. So in reality, volume is less than ideal. And that's what you may see here now. Particles do have size. So if you account for it, you will have two terms, okay? So I recall here what we have. We have two terms. This term A over V squared, which accounts for particle interaction, and term B, which accounts for volume of the particles, right? Of course, you will see if A and B are zero, if they tend to zero, I come back to what? I come back to classical ideal gas law. But otherwise, they show me deviation from ideal gas law, right? So now, remember what we discussed. This is your critical point. Ideal gas law is far away from critical point, correct? So do you agree now that my factors A and B should depend on critical parameters too? Do you agree? This is value B, this is value A. Why? Because yes, if you go away from critical point, A and B should tend to zero. If you approach critical point, A and B should deviate from zero. And this is a formula how they should look like. So you can calculate it. Does it make sense for you guys? Girls, right? Now, why we say it like this? So basically, again, it's still simple equation. So please understand, van der Waals equation, how we call VDW equation, it's a primary way to account for particle size and interaction. This is still simple equation. After equation PV is equal to ZRT when you count for compressibility factor. This is the first nonlinear equation we consider. Of course, there are more complex nonlinear equations. And even there are extensions of van der Waals. For instance, when I am myself work on combustion, if I work on supercritical CO2 turbines, we have so-called Penn-Robinson equation. Also, there is like one equation. There are many extensions of it, but that is the simplest. For instance, here I can show you two more equations like Beattie-Bridgeman equation. Here it is with different constants. And also you have so-called Rubin equation with much more constants. Finally, we have virial equation. I don't request you to remember all this equation, and you may realize that what happens, each new equation gives you more constant and to introduce. Like in ideal gas law, there is no constant. In van der Waals equation, there are two constants, A and B. 5 constants in Beattie-Bridgeman equation. In Rubin equation, you have 8 constants. So they will give you more correct values. And to clarify what's going on, let me do the following now. There is one more very illustrative example that we can consider from your textbook. And this is example number 3, let me see. It's example 3.13. I will show you here. So what is happening here? So example is the following. that people do experiments of nitrogen, N2. So you have nitrogen at temperature 175 Kelvin, and the pressure is 10,000 kilopascals, 10 megapascals. So it's high pressure and quite cryogenic temperature. So it's really far away from ideal gas approach, right? Because temperature is low, pressure is high. For ideal gas, it's vice versa. And for this condition, people measure that measured value is specific for measured value for specific volume is this one. It's 375 meter cube per kilogram, right? So like if this is temperature and this is volume, then this will be your pressure. And now we will consider several approaches what we can do to calculate it, to get ideal gas. To get ideal gas law and other equation, and see are they appropriate here or not. Let me see here, right? So basically that's what we're going to do. So first of all, let's use ideal gas law. So if I use now for ideal gas law for nitrogen, so now it's brute force action, so let me write PV is equal to RT over V. So if I calculate it, I will arrive to what? Here is my R, I get it from the table for nitrogen. Here is my temperature in Kelvin. Here is my specific volume from experiments, and I will come to what? I will come to this value. So what do you want to say? This is experimental value. This is value that I get from my formula. So what will be your conclusion from here? Is it ideal gas? Is it good approximation? No, it's bad approximation. It's very inaccurate. Your error is about 40% here. And it should be like this, yes? Why it's like this? Because you see here, your temperature is very low, your pressure is very high. So it's not ideal gas. So if you employ ideal gas law, you will arrive to almost 14 megapascal, while you have 10 megapascal here. Now, what happens if you will use van der Waals equation? I recall van der Waals equation, right? Here is van der Waals equation. Here, this is your van der Waals equation. So for van der Waals equation, I have this formula for my A, for my B. If I calculate it for nitrogen, I will get what? I will get exactly, so this will be my constant A. This will be my constant B, it's dimension like specific volume. So if I calculate pressure, here will be my pressure for van der Waals equation. It's different. So, and it's big reduction in it. You see why? Because I reduce it first. In denominator, I have B here as compared to ideal gas, so it will be smaller here. And also I eliminate this term. So basically, here what I will have. Is it better? So I believe so. So now my error is only 5%, 5.3%. So you understand now that even van der Waals equation is not brilliant, but it gives you not a bad relation. Okay? It gives you not a bad relation here. It's this value, 5.3%. Correct? What's the next? Next, I have the constants A, B, and C. So if I have Beattie-Bridgeman equation, what would it be? Beattie-Bridgeman equation. So this is my constant A, this is my constant B, this is my constant C for that equation. I don't want to waste a lot of your time for this. And but if you calculate all these values, you will arrive to what? Oh, sorry, I jumped a little bit. I'm sorry for this. Yes, here it is. So if I calculate all these values, I will arrive to what? That for BB equation, I will have here nothing but this value, 10.11 10 megapascals. Do you see it here? Do you agree with me? What would it mean? Well, now the value is even much better. It's 1.1%, a difference from your experimental value that we have. Well, in fact, you know that experiments also are not very accurate, so maybe this value is better than experimental value, right? So it's 1 point. And eventually, if you use Rubin equation, which is even more accurate, then you will see that your pressure that you calculate will be 10.0.9. So which will mean that you have 10 megapascals. which will mean that your error is 0.09%. So that is my conclusion from here. So what do you see here? My conclusion is that what? My conclusion that your pressure is really very close to accurate. That the more complex equation you use here, right? The more complex equation you use from here to here, the more complex equation you use, the better the result you have. Right? On the one hand side, complex equation is hard to implement. On the other hand, it gives you better answer. While, for instance, ideal gas equation is easiest, but it almost does not work all the way. Do we have to know last equation? Well, no, I don't request you to remember last two equations. And of course, I will not give it to you at your exam, but van der Waals equation, I think is good for you to remember and to understand how it look like, to understand how the storms come from. Correct? So that it is. And as you may see here, for van der Waals equation, you have only two constants. For Beattie-Bridgeman equation, you have 5 constants. For Rubin equation, you have 8 constants, and that it is. That's what you should remember and should understand. Any question about this? Any question about ideal gas in general? So that's most important. So now, when you arrive to your exam, I recall you what you should do. Even we talk about ideal gas now, please understand that still ideal gas is not the major topic of this course. First things you should be able to use, you should use tables. So key point for you, you should be able to identify the state, the phase. I discussed it several times. I don't want to repeat it now. You should be able to identify your phase of phases. It's key point. It's most important. If you cannot do it, then it's bad. Do you understand? Now, ideal gas you can use only if you find compressibility factor and only if you have some hint to use it. For instance, air is typically really ideal gas, but if you use water vapor or freon, most likely it's not ideal gas. That's key point. Now, one more hint for you, especially for your homeworks and maybe for your exam. If you remember problem 4 and problem 5 from your homework number 3, what do you have here? Key point there is that you have a process. You have two states, initial state and final state. So you have state 1. So key point is the following. Very often students already know how to identify state 1. So they found state 1 like I discussed earlier. You assume this is saturated mixture and blah, 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 and continue. Assume this is saturated mixture and check. Okay? Now, what do next? What to do next? Then, classical mistakes the student do. Somehow intrinsically you extend this knowledge to state 2, which is wrong. State 2 is fully different. Well, it may be the same state, but typically it's fully different. So if state 1 is saturated mixture, state 2 can be solid, can be liquid, can be vapor, can be saturated vapor, superheated. So for state 2, again, you should be able to solve this problem from the very beginning. Okay? Assume it's saturated and check and show your analysis. You should do it. So, of course, to identify the state, you should know two intensive properties. Remember, pressure and temperature, or pressure and specific volume, pressure and internal energy, volume and internal energy, and so on. You should know at least 2 of them. Please make sure you understand this, okay? Please make sure. Please make sure. Now, well, how sometimes people say, how can I know these two states, state 1 and state 2? Especially how I can know 2 intensive properties for state 2? Answer is the following. Well, read the text. Please understand that from wording you can get equations. Like it can be complex equation like you see here, but equations come from the text. For instance, it's stated that you have a rigid tank, okay? You have rigid tank. What is rigid tank? What does it mean, rigid tank? Rigid tank means what? That volume is constant, okay? So you will have that V2 is equal to V1. Volume is constant. Is this equation? Equation. So it gives you some parameters. Or it can be stated that you have isobaric process, or it can be stated that you have 3-piston cylinder assembly. What is example for free piston cylinder assembly? It's P is equal to constant. So you will have that P2 is equal to P1. So it gives you hint how to solve this problem, true? P2 is equal to P1. Okay. Now, and again, then you can identify the state. Again, read the text. Sometimes it may be stated that it stays with the process is either like for isobaric, like I say here, or isothermal, or isochoric, whatever. If it's isochoric, or you have rigid tank, your volume is constant. V2 is equal to V1. If it's isobaric, or it's free piston assembly, it means that P2 is equal to P1. If it's isothermal, T2 is equal to T1. If it's adiabatic, then Q is 0. Get equation from these statements. It will be really helpful you to identify. Okay, does it make sense? I hope so. So this lecture is time to over, but I recall again, we will have help session, TA help sessions today and tomorrow, and my help session on Wednesday. And also, I believe I will not give synchronized lecture on Wednesday, but I will record it. And basically what I will do, I will introduce summary for exam. It will be like my summary lecture that you can actually listen. And also I will start chapter 4, which actually is some extension of chapter 3 in many ways. Just to consider what kind of process we will consider. We'll calculate boundary work and heat transfer for particular processes, isobaric, isochoric, isothermal, adiabatic. Your exam will be on Friday, so please be prepared to it. Please spend the time left for this preparation. It's most important. I recall it will be on Zoom, like we did for the quiz, so you don't need to come in person. Yes, you have full 50 minutes for the exam, and basically that's why I try to give a task that you need less than 50 minutes, and I will test it on the TA such that, generally speaking, I should write it in 15 minutes, and the TA should give it in 20 minutes. So your exam will be posted at 9:55, and you will have time until 11 to submit it. I don't give more time after 11 because some students have other classes, so they're not able to do it. And again, please realize the following. I know in the exam you should go one by one in the tasks, and you don't expect it to waste time. You don't expect it to think. You expect it to know what to do. If you're stuck in some problem for a long time, it means that you are doing something wrong. And practice, please practice property tables. You need to practice. Even many of you reply to me here, I need to practice. And now you realize if the time is the only concern for you, if you are worrying about time, I know what you should do. You need to practice more. If time is your only problem, you need to practice more. Believe me, the more you practice, the faster you will be. Okay? Any more questions, please? I will stop sharing and recording at this point, but still, I will, in case, I will still have my office hours. In case, and I will stop recording now.